Hello guys, my name is Nuran Sadeh. I'm going to solve with you the first practice assignment. It's about indexing. And before digging into the solution, I need to refresh some points with you from the lecture. Okay, now we have files, and in those files we have our data organized, and our data, they are stored in the form of some records. Okay, what is the problem here? The problem here appears when I need to fetch a particular record. For example, I have written a query where I need to fetch a tuple where name equal Nora and age equal 23. And I have a large DB. So how the PC will work this query? It will go row by row until it hits the tuple we are searching for. Okay, if this tuple is at the end of the DB and the DB is very large, so it takes much longer time in order to fetch the required tuple. So now the performance will be in an O of n. It is not the best solution. It will take much longer time. I have encountered while I was preparing this content, I have encountered a real life example in which a developer was mentioned while they are working on a database, there was a query where it took 8 days to finalize. And when the developer were searching how to improve the performance, they built an index, and this index improved the performance. Instead that the query took 8 days, it took 2 hours in order to finalize. So the index improved the performance in a very efficient way. Okay, so now what is an index? Index is this is those notes I have written, I have collected from the lecture, from the internet, from an older notes. Okay, an index, it is the structure. It's a table, consists of 2 points. It consists of 2 columns. The first one, the key column, it may be the primary key. Remember the primary key we took in the DB1 is the key which uniquely identifies our database, or it may contain the candidate key. Okay, now the second column is a pointer. What is the pointer in this case? The pointer, it holds the address of the tuple or of the record where this key is stored in. For example, I have a record where the primary key equal to 1, name equal Nora, and age equal 23. Here, the key, it will be 1, which refers to the primary key, for example, and this pointer, it holds the address. And this pointer, it holds the address where this tuple, which primary key 1, name Nora, or age 23, is stored. Okay, so now this we knew the structure of the index, and we knew that it makes the performance much faster. It makes the fetching from the DB much faster, so it improves the performance. Okay, now there are many types of the index in this case. The first famous one is the primary index. From its name, primary index, so it uses the primary key or the search key. So it is an ordered file or page, and this page consists of 2 columns or 2 fields. Okay, the first field, as we knew, it is the primary key, and the second field is the pointer in which it holds the address of the block holding this primary key. Also, the primary key is divided into 2 types. The first one is the dense one, and the second one is the sparse one. Okay, now let's talk about the dense primary index. Okay, by talking dense and sparse, in both types, we use the primary key. So the dense primary index. Okay, in case of the dense index, a record is created for every search key in the DB. What is the meaning of this word? Okay, now consider that this is our database. I have 4 records, and this is our primary key. 1, 2, 3, 4. Okay, and this is our index. Dense index states that for every single record in our DB, I have to include for every single record I hit in the DB, this record must be included in my dense index. يعني I have 1, 2, 3, 4 records, then each of those 4 records must be included in my index. So as this is an example, I have in my primary dense index the 4 records in order to reference the 4 records exist in our DB. Okay, now the pros of this dense index is that it is fast because I don't need to go back to my hard disk to my DB. I'm just working on my index because my index contains all of the data I needed. Okay, whatever record I'm fetching for, I'm pretty sure that this record exists here because the dense index reference every single record in the DB. However, the cons of the dense index that it requires more space as I need to store every single record in my DB, so I need much more space because if this is not if this database is very large, not for records, million records, then I need to store in my index million records. So I am going to need much more space. Okay, the sparse index is totally different in this case. The sparse index, records that appear for some records, not all of them. Yani here, for all of the records, I needed to include them in my index. Sparse is unlikely the dense index. I don't have to include all my records into my sparse index. I need to include a record per block. What does that mean? Okay, I have this block. It consists, say, instead of 2 records, instead of those 2 records, it says that this block consists of 50 records. Do I have to include those 50 records in my sparse index? No. I have to include only single entry to reference a block, meaning that I have this contains من 1 to 50 records. I only need to have in my sparse index one entry in order to reference this block. So for this block, I need to have 1, and for the second block, I need to have 3 to reference this block. So I don't have to include all the records in my DB in my sparse index. I only need to include a record per block. Okay, now the pros that I don't need much more space like the dense index because I don't include all my records. I only include a record per block. However, the cons is much slower. Why? Because I don't have all my data in the index here. For example, I need to fetch a record where the primary key or the search key equal to 2. 2 is not available here. So I need to go to the hard disk. And this going to the hard disk, meaning that I'm going to take much more time. Okay, now I have a primary index and I have also something called secondary index. The primary index, as I said, from its name, it uses the primary key. Secondary index is the opposite. It uses the candidate key. It uses any column which doesn't uniquely identify the table. Okay, this is a secondary index. But the index is generated from a candidate key, not the search key. And the last type we have is the multi-level. The multi-level is very straightforward. It is constructed by building an index above an index in this case. Now we are going to solve the questions in the practice assignment 1. So I'm going to start with the first question, true or false. The first one states when a sparse index is used, each record must have an entry in the index. This is, of course, false. Because this is a description of the dense index, not the sparse index. The sparse index indicates that each block or each page must have an entry in the index. Okay. The second one level secondary indices must be dense. This is actually true. The third one, considering 2 levels of secondary indices, any of them can be either sparse or dense. No, false. The first level only, which has to be dense in this case. Okay. Now the fourth one is states that you can only use a sparse index if the table is sorted by the search key, while a dense index can be used for any search key. Search key هنا معناته primary key. This actually is true, as the sparse index indicates or gives you the sense of the location where the data is stored يعني, so they can only work if the keys are sorted in this case. The fifth one, a type of index which is based on any candidate key or a non-key field, حاجة مش primary key يعني, which may have duplicate value and is not clustered or sorted by this key, can be classified as primary index. This is of course false, عشان ال primary index من اسمها it is based on the primary key or the search key, not the candidate key. So it will not be a primary index, it will be a secondary index. Okay. Okay, now going to question 5. For the given dummy relation below called fiction character, this is our table. Do each of the following. Page is a relation appropriately, assuming a page can hold 2 records or 4 key pointer pairs. Okay, forget about point 2 or 3. I'm going to start with the first point. Now, paging the relation, meaning we need to map this table, okay, in 2 pages. And the question states that the page holds up to 2 records and the page or the block while constructing the index can hold up to 4 key pointer pairs. Yani, while mapping our table or our relation into pages, okay, on the hard disk, each page will hold normally 2 records. Okay, المقصود ب 4 key pointer pairs, 4 key pointer pairs here, that each page per index while constructing our index بيكون في pages. This page will hold up to 4 key pointer pairs, as we know the index consists of 2 columns. The first column is the key, which is maybe the search key or the primary key or the candidate key, and the pointer, which here points to the address of our key on in the data files on the hard disk. Perfect. So the first part of the question is very straightforward. We will just page this table into blocks. Okay, so this is paging the relation. It's very straightforward. We have each page consists of 2 records, and we have the total number of records we have per relation is 8. So we have 4 number of pages to hold our data on the hard disk. Okay, going back to question 2, to the second part, sorry. In question 5, we need to construct a primary, secondary, dense, sparse, and multi-level indices, and briefly explain what data columns can be chosen for each type of index. Okay, perfect. I'm going to start first with the primary index. من اسمه primary index, meaning that we will use the primary key or the search key or the key which is uniquely identifies our table. In our case here, this is the char ID. This is a unique ID. Perfect. Okay, now going back to the solution, it's very straightforward. Also, these are our pages. Now we constructed in the first part, and this here our index. Okay, our index, the primary index, consists of 2 pages. Okay, ليه حد يقول لي الانdex ده consists of 4 records? Because according to the question, it says that a page can hold 4 key pointer pairs. فهو محدد while constructing an index, البيج في الانdex ده هتhold how many records. Okay, so now we will have 1, 2, 3, 4 to reference here the values in our pages, and 5, 6, 7, 8 to reference the other 4 values in our pages. Now this is dense. Why dense? Because according to the definition of the dense index, that we need to include every single record in the data file in our index. So we have total number of 8 records in the data file, and we included all of them in our index. So this is a dense index. So now we satisfied primary and dense index. Okay, how many page and how many number of pages to construct the primary index? 2. This is the first page, and this is the second page. Okay, going back to the question. Sorry. Okay, we need to construct secondary index. Okay, now while constructing secondary index. Okay, now the secondary index, we need to use a column rather than the unique column, meaning that while constructing a secondary index, we can't use the primary key or the search key. We should use the candidate key. So we can pick any column which doesn't uniquely identify our table. I'm going to pick the age column. okay, while constructing the secondary index. Okay, please take into consideration two important points while we are constructing any index. The index, the records per index must be sorted, and we can't include duplicates while we are constructing our index. So we can't have duplicates in the index, and the records in the index must be sorted. Okay, perfect. And now we are going to construct a secondary index with an age column. And first, I'm going to sort those values for the sake of index. لكن paging the relation لا عادي هيكونوا زي ما هم. However, for the sake of constructing the index, we need to reorder the values in the age column. Okay, this is our secondary index. Here I said that we will pick another column instead of the primary key, which is a char ID. For example, we can pick an age. I sorted the age values here, 28, 32, 39, 54, 58, 61, 65, 73. Okay, paging the relation is normal. However, هنا I didn't include the primary key or char ID because I don't care about them here. I included هنا 73, 54, just like the normal table. Oh, 73 and 54. Okay. البيجنج ريليشن زي ما هو زي ما we page the relation from question 1 هيكمل معانا till the end of the question. فهنا البيجنج زي ما هو. However, الاندكس secondary index have الvalues بتاع الage column and the values are ordered ascendingly. Okay, and each pointer here points to the address of the record in the data files on the hard disk. How many number of pages we have while constructing the secondary index? There are 2 pages. And actually, this is also dense. Why? Because we referenced every single value of the age column, right? It's not a sparse, it's a dense index in this case. Okay. Okay. Returning to our question. Now we finalize the primary, secondary, and dense. Dense, the primary index and secondary index we constructed, they are already dense. We finalize the first 3 points. Now going to the sparse index. The sparse index, it is quite different from the dense index. In the dense index, we refer to every single record in the data files. However, in the sparse index, we refer to every single block. Meaning, if the block consists of 3 records, I need only 1 record to refer to this block. Okay? Okay, this is a sparse index. I have normally our paging. And please take into consideration while constructing the sparse index, we pick the primary or the search key, which is a char ID. Now, as I said, I don't reference all the 8 records. I only reference the blocks. So I have 4 blocks. So I am going to reference, I'm going to have, 4 values in my sparse index. So this block, I'm going to pick only single value to reference it, which is 1. This block 3, this one is 5, and this one is 7. So how many pages we have in order to construct the sparse index? Only 1 page. Okay, going back to the question. We need to construct the multi-level indices. The multi-level indices is very straightforward. We build an index above an index. من اسمها, we have many indices. Okay, now please take into consideration if I have a multi-level indices, the first one, the only dense index can be constructed in the first level. Okay, and the remaining indices will be sparse indices in this case. That's why here I constructed a multi-level. This is the first level. As I said, it's dense, meaning that I have all the 8 records in my dense index. And then the second level, which is this one, this is the second level. It's the sparse one, meaning that it contains values to reference blocks, meaning I have 2 blocks, so I'm going to have 2 values to reference those 2 blocks. Here, 1 to reference the first block and 5 to reference the second block. Now, the last part of question 5, in case of a dense primary index is constructed, Show the steps of inserting the following topic. Okay, inserting is very straightforward. Okay, now we have our pages, our 4 pages, and we know that each page holds up to 2 records. لحد 8 we have full pages, so we need to construct a new page to handle the new added tuple. Okay, and as said by the question, it is a primary dense index, so we used the char ID, which is our primary key, and dense, so we referenced all our records in this primary dense index. And we have 2 pages, they are already full with 4 key pointer pairs. That's why we constructed a new page in the index, and it has only single value, which is 9, to reference the newly added tuple in this case. Okay, now returning back to the question, we need to delete record number 3. Also, deleting is very straightforward. We will shift the values and then update the index. What I mean by shifting is, now here I had 5 pages with 9 records, right? I'm going to shift those values in order to get rid of the third value, which is here, is Wonder Woman Truth Way Paradise 39. Okay, so we will have 4 pages, and we will end the page with mini, Tweety, shifting, and we are not going to see Wonder because it's already deleted. It's shifted. جه مكانها, it is replaced by Donald in this case because of shifting. Okay, in the pages we shifted the values and we removed the record number 3. Now, what happens in the index? The index is also updated. Here we had a 3rd page in the index. This page is removed because of the shifting thing we did in the pages, and here the index will, as it's a primary index, the primary index referenced, the primary dense index referenced all the values in our pages successfully. Now, for updating Tweety's age, it's very straightforward. You will search for Tweety and update its age, and no update will be done in the index in this case. Thank you. Now, going to question 4, assume that a page can hold up to 2 rows if we have a table D with 16 rows with the following keys. Okay, build a 3-level index on D, one of which must be dense. Clearly explain how you handle duplicates. Okay, now we will first map our table, this table, which consists of 16 rows, to pages. And according to the question, a page can hold up to 2 rows. Okay. So the first page, for example, it will contain 50, 80, وهكذا. Okay, now building a 3-level index on D, one of which must be dense. Please take into consideration that the only level that can be dense is the 1st level. Okay, not the 2nd, not the 3rd. Okay, going back to the solution. This is the mapping from a normal table to pages, and according to the question, we said that the table holds up to 2 rows. That's why we map the table into 1, 2, 3, 4, 5, 6, 7, 8 into 8 pages, in which every single page holds up to 2 records. Now, going back to the index, now we have, according to the question, we need to build our data on a 3-level index. So we have 3 indices. And the question stated that one of which must be dense. So as I said before, only the 1st level can be dense. That's why the 1st level here is a dense one. Dense meaning that every single data entry in the pages appears in the 1st level index in this case. Okay, now please take into consideration that the index is sorted. Okay, and also the index doesn't contain duplicates, meaning it's a dense index. Yes, we need to reference every single entry in the pages. However, we don't refer to the duplicates in this case, meaning that I have 50, then I have 50 here, then I will add it in the dense index. 80, I will add it. 100, I will add it, and then I will hit another 100. I will not add it into my dense index because the index doesn't include duplicates in this case. The index only refers to the first data entry and doesn't refer to the duplicates in this case. And we will include all the data excluding the duplicates, of course, in the first level dense index. Now, going to the second level dense, to the second level index, it's a sparse index, meaning that I need only single data entry from the block in order to reference it in this sparse index. Here I have block 50 and I have a block contains 50 and 80 records. Then I will need only a single entry to represent this block in the sparse index. So I chose 50. Here I have 100 and 150, and I need only a single data entry to represent this block in this sparse index. I picked 100, وهكذا. And the third index also, it's a sparse index, and we need a single data entry, as I said before, to reference this block. Then from this block, I will pick 50. From this block, I will pick 200, and from this block, I will pick 430. Now we have finalized our question 4. Okay, now going to question 2. Suppose blocks holds either 3 records or 10 key pointer pairs as a function of n. Find the number of records and how many blocks do we need to hold a data file, and how many blocks do we need to hold the dense index and sparse index. Now let's divide the question into 2 parts. The first part, we need to know the number of pages or the number of blocks we need to hold a data file. And we know, according to the questions, that the data is a function of n. So we have n records, and we know that the page holds, or the block holds, up to 3 records. So how many pages we need to hold those n records? We will need n over 3 pages. How? Consider that we have a total number of records equal to 15. This n equal to 15, and we know that the page holds up to 3 records. Then how many pages do we need to hold those 15 records? We will need 15 divided by 3. So we will need 5 pages in order to hold those 15 records, taking into consideration that each page holds 3 records. Okay, so for the first part, the number of pages we need to hold the data file equals to n over 3, which is n is the total number of records, and 3 is the maximum number of records a block or a page can hold. Okay, this is straightforward. Now, we need to go to the second part of the question. How many blocks do we need to hold a dense index? Now, referring to a dense index, we need to remember that when we are constructing a dense index, we need to include every single data entry we hit in our pages. Meaning that I have n data entries, then I will need to reference those n data entries in my dense index, all of them. So it's quite similar to the number of blocks we need to hold the data file. Okay, we need to know how many records a page can hold while constructing the index. The question said 10 key pointer pairs, and we know that by writing 10 key pointer pairs, we know that he is talking about the total number of records in which a block can hold in the index, in this case. Okay, so we know that while constructing an index, the page can hold up to 10 records. So we will need n over 10 blocks or pages to hold the dense index in this case. So this is our dense index. This n is the total number of records we have, and 10 is the maximum number of records a block can hold while constructing a dense index. So we will have n over 10 blocks in this case. And the total number of blocks we need, including holding the data file and including holding the index. So we will have n over 10 plus n over 3. It will be 13n over 30 in this case. Okay, now going to the second part, the sparse index. How many blocks do we need to hold the data file? It is the same in the first part and in the second part. It will be n over 3. However, the sparse index is unlike the dense index. In case of the dense index, I said that I need to include all the data entries in my dense index. However, it is unlikely in case of the sparse index. Why? Because the sparse index, we need only single data entry to reference a block in the sparse index in this case. For example, I have a block of 3 records, 50, 80, 100. While constructing the sparse index, I will only need the 50 in this case. So I will need to reference the blocks, not to reference the records themselves. In the dense index, I need to reference the n records. However, in the sparse index, I will need to reference the number of blocks in this case. And I know that how many blocks we need to hold the data file. They are n/3, n/3 blocks. And I need a single record per block to construct the sparse index. And again, the page per index can hold up to 10 key pointer pair, meaning that the page per index can hold up to 10 records. So I will divide by 10 also, but I'm not going to divide n by 10 because I don't need to include all the n records in my sparse index. I will divide n/3 by 10. As I said, I don't need to divide n/10 in case of the sparse index because I don't need to include all the n records in my sparse index. I only need to include a single record representing a single block. That's why I have n/3 blocks. So I will divide n/3 by 10 because I need to reference every single block I had into my sparse index. So I will have n/3/10 blocks in order to hold the sparse index, and the data file is equivalent. It is n/3. That's why the total number of blocks to hold the data file in sparse index will be n/30 plus n/3, which will be 33n divided by 90. Then we finalize question 2. Okay, now for question 3. Repeats the exercise above if we use as many levels of index as is appropriate until the final level of index has only one block. Okay, so we need to calculate how many number of blocks do we need to we need to calculate how many number of blocks or pages to hold those level of indices. Okay, now question 2 consists first of a dense index, second of sparse index. So we are going to solve for the first part, dense index. Now, if we need to include a dense index in a multi-level indices, so the dense index must be constructed in the first level. Again, if we need to include dense index in a multi-level indices, so the dense index must be constructed in the first level of those multi-level indices. Nice. Okay. So the first level, it will be a dense index, and we calculated the dense index in question 2. The number of blocks to hold those dense index equal n/10. So we know now a part of the solution, and we also know that according to the question, final level of index has only one block. So we know that we have another one block to hold those multi-level indices. However, the other levels, we don't know how many blocks we need to hold them. So this is the dense index, n/10 pages. Okay, and this is the final level. According to the question, the final level consists of only one block. But why I included 10 records in this final level block? Because according to the question in part 2, as question 3 is just a repetition. In part 2, we know that the blocks holds 10 key pointer pair in case of indices. That's why here, in this final level index, this block holds 10 key pointer pair, meaning it holds 10 records. Nice. And we know that only the first level is a dense index, meaning that the other levels are a sparse index. Okay. So, referring to the sparse index, every single record will refer to a block, not to a record. So we have here 10 records, and every single record will refer to a block. So if this final level consists of one page, This level consists of how many pages? It will consist of 10 pages, 10 blocks. Why? Because every single entry in the final level refers to a block. So we have a total of 10 records. So we have here in this second level 10 blocks. So in the solution here, I included one page here to count the final level, and 1 times 10 to include this second level. 1 times 10 meaning we have 10 blocks, because every single entry, as I said before, refers to block. Now, each block consists of 10 entries. Now, every single entry will refer to a block. So for example, if I'm going to talk about this block, and those are 10 blocks, this block consists of 10 entries, and every single entry will refer to a block. So this third level will consist of how many blocks? It will consist of 10 times of 10, because every single block of those 10 blocks refer to 10 blocks. يعني البلوك دي consists of 10 records. كل record فيهم they refer to a block. That's why 10 multiplied by 10. So this the third level from the left, it will be 1 times 10 times 10 plus, and we will continue to the same until we hit the final level. Until we hit the first level, and the first level is the dense index, which is equivalent to n over 10. Okay, so we know now this equivalent to 1 plus 10 power 1 plus 10 power 2 until we hit n over 10. Actually, this equal to 10 power 0. So we need to know this is 10 power 0 plus 10 power 1 plus 10 power 2, and until we hit n over 10. We need to know this one equivalent to 10 power cam. So I wrote it down, n over 10 equal 10 power x. So we need to log both sides to the base 10. Log base 10 n over 10 equal log base 10 10 power x. This x will fall down. It will be log base 10 n over 10 equal x log base 10 10. This one equivalent to 1. Okay. Therefore, x, it will be equivalent to log base 10 n over 10. So now, if we need to know how many blocks to hold those multi-level indices, it will be the summation of I equal 10. I here refers to the power, because 1 equivalent to 10 power 0, as I mentioned before, will be I equal 0. لحد هنا, this equal 10 power x. We knew now in the x equal to log base 10 n over 10. That's why I it will be here a log 10 and log base 10 n over 10 power I pages to hold the multi-level indices, plus n over 3 to hold the data file, to map the table which contains n records into pages where each page consists of 3 records. Perfect. Now we repeated the third. According here, we repeated the exercise above, the first part, the dense index. Now we need to repeat the exercise 2 according to the second part, the sparse index, by constructing multi-level indices. It will be exactly the same. Instead, that, as I mentioned while we were answering question 2, while we are constructing sparse index, we don't divide the number of records divided by 10, because we don't need to include all the records in our sparse index. We only include a single entry per block, and we have total number of blocks to hold the data equivalent to n over 3. That's why we divided n over 3 by 10, and all the other the summation and the n over 3, it will be the same as the second part, which is a dense index in this case.